Hello, welcome to episode 5C-ish, I think, of multivariable physics. Today I'm going to actually touch on something that I completely glossed over and have been avoiding, and that is the derivative of vector functions. Like, is there a better way to kind of express that? So, there is, and we're going to call it the total derivative d, and we're going to apply it to some function f. Okay. And so what is this d? Well, this is simply the gradient, because if you remember, f is equal to f1, f2, dot dot dot, right? Then we have to consider all of these functions, f1, f2, they all have derivatives. So we want to consider we want to consider f1, right? x1, f1, x2, f2, x, or f1, x3, and so on. We also want to consider f2, x1, f2, x2, right? So this is going to come out being it comes out as a matrix, a really big matrix. So if f is a vector from r to the n to r to the m, d is an r n times m. It's an n times m matrix. Okay. And so what is this? Well, this is, if you notice that we're taking the same function and we're taking all of its partial derivatives with its, all of its parameters, and we're doing that for every function. Well, that's just the gradient, right? Or the gradient transpose of f1, gradient transpose of f2, and so on and so forth, right? And that's all that total derivative is. That's just we take the gradient transpose of every individual component. And this also has this another special name. It's called the Jacobian. It's called the Jacobian. And it is simply a matrix of all different, of all the partial derivatives. Right. For example, this is an example in 2 dimensions, right? And yeah, so that was a very quick episode. I probably should have touched on this earlier. The only reason I delayed it was because I wanted to talk about when it comes to the tangent plane approximation or the linear approximation of a vector function. Well, this linear approximation is going to be f of x plus h, some h vector, is equal to f of x, as we know, right? Plus the total derivative f of x times h. Now, if we think about this, this is a matrix, Rn matrix, or Rm vector. This is an Rn vector. This is an Rn by m matrix, right? You apply these, and then you're going to end up, the result is going to be an Rm vector. So that's kind of, I want to talk about linear approximations first before I talked on that, so that kind of makes sense. Next, we want to consider the chain rule with this, and the chain rule for vector valued functions follows pretty much the exact same intuition. I should make some room somewhere, but chain rule we have the total derivative of f of g of x. This is equal to the total derivative of f, right, gx times the total derivative of g of x. This becomes a matrix multiplication where so f is from p to n, or yes, p to n, and then g is going to be from n to q. Actually, I got these swapped. Actually, this is actually u r p to n, and then yeah, I have these swapped. It's not f of g of x. It's actually let me quickly fix that. Let me just fix that very quickly. We have f is going to be from r to the m to r p, and then g is going to be r to the q to r m, and then so this matrix, this is going to be r or m times q, and this is going to be q times m, or other way around. Actually, it's going to be p times m, and this is going to be m times q. So this whole thing becomes p times m. Or p times q. Sorry. P times q matrix. I know it's a bit sloppy, but it makes sense. And so that's the total chain rule for these functions. And yeah, so I've been avoiding that, but I just wanted to touch on that. So that's that. Next up, we'll probably be talking about optimizations and then quadratic approximations after that. So, cheers.